Today's opening lesson is an engineering lesson, something I learned from a friend of mine many years ago. Shortly after I finished college, he went into engineering and he said, I don't know how to do something. What I do first is I go ask somebody else who's already done it. This is a big lesson for today and in general for those of you that are engineers. Here's an example. Here I have two nails, and suppose I have the problem of balancing one nail on the head of the other. Can I do that? It's kind of difficult, actually. You got to do this just right. Let's see. There we go. One nail balanced for a moment on the head of the other. But now the problem comes along, can I balance 10 nails on the head of one? How do you do that? The answer is you go ask your friend. I looked it up in the book. So here it is. Pound one nail into a piece of wood so it's real rock steady. Then you put lay one nail across, lay these four on this side and these four on this side, and put one nail on the top between them, and sure enough you can balance 10 nails on the head of one. I didn't actually have too much trouble with this once somebody showed me how to do it. So today I'm going to try and show you how to do some difficult volumes that maybe you didn't think you could do before. And I'll remind you first of all, better not slip on that nail, huh? What we were doing last time, we said we could evaluate volumes by doing double integrals. Remember in Calculus 1 you could do a single integral of a function of one variable over an interval of the x-axis. Now what we're doing is a double integral over a plane region. So we said we could integrate over plane regions like this, or this were the most important types. This was a vertically simple region, or type 1 region. It had vertical lines on the side, x equals a, x equals b, and then a curve on the bottom, y equals g1 of x, and a curve on the top, y equals g2 of x. Or we could do, you know, what's sacred about doing this in the x direction, we can do it in the y direction. We have a horizontally simple region between y equals c and y equals d, and two curves, x equals g1 of y and x equals g2 of y. And we said in that case, there's a nice theorem that says these double integrals over these plane regions can be evaluated as iterated integrals. On the inside, for the vertically simple region, from the bottom function to the top function, bottom curve to the top curve, g1 of x to g2 of x, and on the outside, from the min value of x to the max value of x, whatever the integrand is, dy dx, and if f of xy is the height of a surface, that was the volume below the surface and over this plane region. But more generally, it can actually be something else. For instance, if f of xy is the density in, say, kilograms per square meter, of a flat lamina, we call it sometimes, something that's so thin we can treat it as a two-dimensional object, we can integrate over that region the density, and this actually gives us the mass of this flat plate. Now the other alternative to integrating over a plane region is we could integrate y going from c to d, these two horizontal lines, left function to right function. X equals g1 of y to x equals g2 of y. The trick, put a horizontal line here, the one that intersects on the left tells you what g1 is, the one that intersects on the right tells you what g2 is. And this one will evaluate a double integral by theorem for a type 2 region, or horizontally simple region. So here's a short example. Let's just set up a double integral on this one. To integrate, maybe this is a density function, or maybe something else. 2x minus y, in fact this won't be a density, it'll be negative over part of the region. 2x minus y over this triangle right here. It's bounded by the line y equals x, the line y equals 1, and the line x equals 0. That's my region R. How can I set that up? Well, I want the double integral of 2x minus y dA. I can rewrite that by theorem as a double integral. Let's treat it as a vertically simple region. So x on the outside, x goes from its min 0 to its max 1, 0 to 1 on the x-axis, and then y goes between the two curves, y equals x and y equals 1. So y equals x, this one, and y equals 1. That one is the bottom curve and the top curve. 2x minus y dy dx. There it is. There is an iterated integral by which we can evaluate this double integral, because now the integral on the inside holds x constant. That's an easy thing to integrate, right? 2x minus a constant. Remember, we hold y constant, x constant in the integration with respect to y, so it's 2c minus y integrated with respect to y. That's easy, and then we get a function of x coming out, and we just integrate that by calculus 1 with respect to x. The other way we can do this, however, is to integrate y going from c, y equals 0, to d, y equals 1, bounded by two horizontal lines, this one degenerating to a point. And between a left curve, well, let's say that's x equals 0, and a right curve has to be x as a function of y, so rewrite y equals x as x equals y. So I'm going to integrate now from the left curve, y equals 0, to the right curve, x equals 0, to the right curve, x equals y. And then y going from its min 0 to its max 1, integrate with respect to x on the inside, y on the outside, does the horizontally simple region. So that's how we can do these double integrals. And then we said we could use these in one special case to find volumes. I'm going to extend the theorem we did last time. We said if you just integrated f of xy and that was not negative, you could get the volume below the surface and over the xy plane. More generally, what you can do actually is this. If f1 and f2 are integrable on a region R over which you have a top surface and a bottom surface of a solid, bounding a solid, then you can take the double integral of f2, the top surface, minus f1, the bottom surface, hence f1 less than or equal to f2 here, and get the volume between the two surfaces and over the plane region R of projection. So let's just do a simple example. Find the volume of the solid with top surface f of xy equals xy, and bottom surface f of xy equals 0 over this plane region here, which is bounded by a parabola and two lines. Well, this isn't too hard. This is the same problem as last time. The bottom is actually just the xy plane again, so it amounts actually to this integral of the top surface minus the bottom surface by this theorem. Is the same thing we had before, just integrate the top surface over the plane region when you're just integrating above the xy plane. So we have to integrate xy over the plane region. Now, by the theorem, we can rewrite this as a vertically simple region, right? We can say x goes from a min value of 0 to a maximum value of a. Meanwhile, y goes from a bottom curve, y equals 0, to a top curve, y equals a squared minus x squared. Now, I haven't even said what a is. What this does is it gives you a hint. You can actually use these integrations to find formulas for areas of plane regions or volumes of surfaces over plane regions using this technique. Because you can put arbitrary letters in here, and here's the area below a parabola of the form a squared minus x squared, and volume below a surface xy and over this region bounded by the parabola and lines. So the theorem says we can do this, rewrite it as an iterated integral, and now remember the iterated integral, the inside integral is a partial integral, treating the other variable x as a constant. Now, if I'm treating x as a constant, I can pull it out of this integral here, right? It's a constant. I'll just pull it out. And now I've got integral from 0 to a of x, integral from 0 to a squared minus x squared y dy dx. Now, what's the integral of y? That's easy. It's just y squared over 2, right? And then I have to plug in the endpoints and take the difference. This is applying the fundamental theorem of calculus from calculus 1. And when I put that in, I get a squared minus x squared squared over 2, right? I'm plugging in this for y squared and dividing by 2. Plugging this in for y divided by 2. Now, I need to integrate x times this mass. We can multiply this all out and make it a messy polynomial, and it's not actually all that hard to integrate, but what's even easier, I think, is to make a substitution. When you see a squared minus x squared squared and almost its derivative here, we could substitute u equals a squared minus x squared. Then du is the derivative of that dx minus 2x dx. And it came off the end here a little bit, but in that case, multiplying by minus a half we've got minus a half du can replace dx directly. So I'll replace dx with minus a half du. I'll replace a squared minus x squared with u, so I have u squared over 2. And then the x dx becomes the minus 1 half du, I should have said. But now you have to change the endpoints too, right? When x equals 0, that means u equals a squared minus 0 squared is a squared. So the bottom endpoint is a squared. When x equals a, then u is a squared minus a squared is 0. So this will now go from a squared to 0. Well, I multiply this out. The 1/4 can come out. The minus, I can do this trick. Minus the integral from a squared to 0 is plus the integral from 0 to a squared. I'll switch the order and get rid of the minus sign. Now I just have to integrate u squared with respect to u, which is u cubed over 3. Plug in a squared and 0 and take the difference. So I'll wind up with a squared over 12 is the volume of this solid below the surface indicated and over the region bounded by the parabola and lines. So there's something maybe you didn't think you could do before. This is actually of fundamental importance in lots of engineering applications, right? Not every piece of metal you cut is rectangular. If you cut in that odd shape, and this is your density function here, this is the kind of integration you would have to do. Here's another one. Let's find an actual volume below this function, f2 equals 6x squared y, and over the function f1 equals 0. Again, I'll just make it easy, make it the xy plane, but the point is you can make it anything in general. But now I'm going to put it over this type of region. This type of region poses a new problem because it's not so nice as a vertically simple region. It can be written as a vertically simple region between x equals 0 and x equals 4, this top curve and this bottom curve, but now the top curve is piecewise defined. I'm going to have to break my integral into two pieces to make this a vertically simple region. I'll have to integrate from here to here with this on the top and this on the bottom, and then integrate from here to here with this on the top and this on the bottom. Double my trouble, right? So I don't want to do that. Instead, I recognize that if I just make this a horizontally simple region, I can use this curve on the this minimum value of y, 0, this maximum value of y equals 2, and just go between one consistent left curve and one consistent right curve. What is this curve? Well, it goes from 0, 0 to 2, 2. It's the line y equals x. This is the line x equals 4. Let's go to the next page. So to integrate, to find the volume, I integrate top surface minus bottom surface over the plane region that its projection is. By the theorem, we can go from the left curve to the right curve. X is a function of y, so instead of writing y equals x, I'll write x equals y, and the bottom limit is y. To the right curve is x equals 4, so I go from x equals y to x equals 4 on the inside, and then minimum y to maximum y on the outside. That's the type 2 region. So now I can do it all in one fell swoop if I use a horizontally simple region. I just have to integrate this. Once again, I notice now on the inside integral with respect to x, y is treated as a constant, so I can pull it out and put it out here. That makes my day a little easier. Also, the 6 comes out. I just have to integrate x squared and get x cubed over 3. Plug in the endpoints and take the difference. I wind up with this. Now, how do I integrate that? That's calculus 1, right? So here's my steps going through in evaluating this by calculus 1, and I get 1216 over 5. So not so bad. Those integrals, just remembering the inside one is a partial integration. It's just calculus 1, and not so bad. However, you notice sometimes there's an advantage integrating in one order or the other depending on the plane region. There can also be an advantage integrating in one order or the other because the integration might be easier if one's on the inside than if the other's on the inside. So let's see what can happen in that case. We want to be able to switch the order of integration, right? Between x on the inside, y on the outside, to y on the inside, x on the inside, or vice versa. Here's an example of doing it. This one we could do in either order, actually. Suppose I had this double integral that somebody gave me. And I said, boy, that looks tough. Maybe I want to integrate that in the other order. What what can I do? Alright, I'm not quite sure how to integrate this maybe, but if I do y first, maybe it's easier. Here's what I can do. I first sketch the plane region. So to switch order of integration, you just sketch the plane region, and then use that plane region to figure out, just like you did before, what's the corresponding result for the other type region. So with this x on the inside and y on the outside, y is going from 0 to 6, and x is going from x equals square root y, which is this one, to x equals square root 6, which is this vertical line. So I sketch that region and say, if this is on the left and this is on the right, and y goes from 0 to 6, this must be the region in question that I'm integrating over. So to switch the order of integration for a double integral, first sketch the region, then say, well, if it's the other type of region, a vertically simple region, I go from this vertical line, x equals 0, to this one, x equals square root 6, on the outside, and bottom curve to top curve on the inside. X equals 0, I rewrite x equals square root y as y equals x squared on the top. So bottom curve x, y equals 0 to top curve y equals x squared, x equals minimum to maximum value on the x-axis. It's rewritten in this in the opposite order. This is actually a little easier because this could be integrated with respect to y by a substitution. So the inside integral is a little better. Here's another note, just in passing, that you should be aware of. If you're finding the area of a plane region, this double integration actually gives you a way to find it by a double integral. So for instance, if I have a plane region R here, I could actually find the area if I can just write the double integral over R by integrating 1. The reason being, remember that this gives you, if I integrate 1, the volume of the solid whose height z is 1 everywhere, and whose base is the region R. Well, the volume of this solid is just base times height, R times 1. So it follows that I can get the area of the plane region by doing the volume of this solid of height 1, which is just a double integral. Here's a very trivial example. Suppose I didn't know the area of a triangle, this triangular region here, because it was set up as this double integral. Well, it's double integral of 1, so I know it's just the area of whatever plane region this integrates over. So I'll write it as double integral over the plane region, dA, and then I'll draw the plane region based on this. X goes from 0 to 2, min to max. Y goes between y equals 0 and y equals 1 half x. I know those, that's a line and a line. So I go between the vertical lines x equals 0 and x equals 2. Between these two lines, y equals 0 and y equals a half x. Now I recognize it's a triangle that I'm integrating 1 over. So this is actually just, this double integral of 1 is just the area of the triangle. It's 1 half base times height, which is 1 half 2 times 1 is 1. This is a double integral that's equal to 1. Finally, today we want to look at the triple integral. We'll at least get started. Next time we'll do the interesting stuff. I have an even better problem for you to open tomorrow. Just like TV, I'll try and lead ahead to make you watch the next show. The triple integral over rectangular blocks will be performed in nice analogy to what we did with double integral over a rectangle in the plane. We'll say that the triple integral over a box B in 3 space will be defined to be a limit of a triple Riemann sum. K going from 1 to P, J going from 1 to N, I going from 1 to M, where I've partitioned the X interval here, A to B, into N pieces, the Y interval from C to D into N pieces, and the Z interval from P to Q into capital P pieces. So it's little n equals M times N times P, and I'll take the limit as the number of sub-boxes when I break this into an N by P bunch of little sub-regions. take the limit as the number of boxes goes to infinity of the sum of f at any interior point, say xk star, xi star, yj star, zk star, inside the ijkth box. So it's got width delta xi, width delta yj, well the height delta zk, and its volume then is this, delta xi, delta yj, delta zk, and if I take f times that, I'm going to say that's the triple integral when I sum and take the limit of this function over the box. And you notice, interestingly, if you put f equal 1, then you're just integrating the sum of the little subvolumes, and actually you get the volume of the box. So it's just like you can do a double integral of 1, get an area, you can do a triple integral of 1, and get the volume. In this case, just for the rectangular box, but next time we'll do more general solids in 3-space, and it works for that too. So here's the definition of the triple integral. It's just like the definition of the double integral with one more sum, right? And the integration is of the volume of the typical box instead of the typical rectangle, multiplied by a function of 3 variables instead of a function of 2 variables, at an arbitrary interior point. Now, if f is continuous, then it turns out it doesn't matter which interior point you pick, and it doesn't matter how you partition this, as long as in the limit as n goes to infinity, the width, length, and height in all 3 directions goes to 0 in your partition. That's implicit in this definition, actually. You'll get the same number. If you get the same number, that makes sense that you want to define the definite integral this way. And Fubini's theorem says, in fact, you can evaluate that by taking a triple iterated integral. Let x go from a to b, y go from c to d, and z go from p to q, the limits of the box. F of x, y, z, dx, dy, dz is completely analogous to Fubini's theorem over a rectangular plane region. Now you have it over a rectangular box in 3-space with just one more integral. And actually, just like you could do the rectangular region in either order, you can do this in any one of the orders by switching these 3 integrations around to whatever order you want. There's 6 possible orders, if you think about it, for integrating. So here's a simple example. Suppose a rectangular box of width 1, length 2, and height 3, x from 0 to 1, y from 0 to 2, z from 0 to 3. It bounds a solid, and maybe this is the density of the solid, x plus z, in kilograms per cubic meter of that rectangular solid. What is its mass, I wonder? Well, we're going to say that the triple integral of the density actually gives you the mass. So let's see. The triple integral of the density, x plus c, over the box by Fubini's theorem says I can integrate x going from 0 to 1, y going from 0 to 2, z going from 0 to 3, the 3 limits of the box, dx for these limits, dy for these limits, dz for these limits. And to do the integral, I notice immediately, since I'm going over constant endpoints, there's no y in here. I can just pull this dy clear through, since all this stuff is treated as a constant in this partial integration here. So, I pull the dy through. Now I just have a double integral times the integral from 0 to dy, which is 2. Right? This is y, plug in 2 and 0 and take the difference. I integrate x plus z, treating z, the outside variable, as a constant. And I get x squared over 2 plus, treating z as a constant, the integral is the constant times x, is xc. That needs to be evaluated at x equals 0 and 1 and take the difference by the fundamental theorem of calculus. I get 1/2 plus z. And then calculus 1, integrate with respect to z. At the end, I wind up with 1/2 z plus 1/2 z squared, evaluated at 0 and 3 and take the difference. This whole thing just comes out to be 12 kilograms. So try these, and we'll do much more with this next time we're going to find some real fascinating formulas for all sorts of solids. You always wonder, where does the volume of a sphere come from? That formula we see 4/3 pi r cubed. How can I figure it out? It's calculus.